Let's take a look at this problem. I'm not going to actually go through it at this very second. We will in a moment. But more importantly, I want to know, what is it? What does it mean? What are we looking for? When I say solve that thing, find the solution of that linear system, what is it? What does that mean? Okay, now each of those, if I look at these separately, that top one is a line, isn't it, if I graph it, right? We won't bother with graphing it correctly yet, but that's a graph of a line. So if I were to graph it, it would look something like, that one would look something like, this-ish. Maybe not exactly, but it's going to look something like that. Okay? What about the other one, the bottom one? It's a line also, isn't it? Right? Okay? Now, if I graph the bottom one, I'm going to get a little different line. I'm going to get a line that maybe looks something like that. Okay, so if I'm looking for the solution of this, what's it going to be? What do you think? I mean, if I want to find a solution of this line number 1, I should have made up different colors. That was kind of dumb. If I want to find a solution of line number 1, I'm going to have to find an x and a y value that work for that equation, right? So for example, for this first one up here, if I take x to equal 1, then what's the y value that would go with that? If I plug 1 in for x, what's the y value I would get that would go with it? Okay, what I'm saying is if I plug an x value of 1 in to that top one, I'm going to get 2 times 1 minus 4y equals 13. Yeah. Right? So if I want to solve for y, like we were doing yesterday, how would I isolate y? Okay, I'm going to subtract, that's 2, right? I'll subtract 2 to the other side. So I'm going to get minus 4y equals 11, right? And then what? Divide by negative 4. So I get y equals negative 11/4. So there's the y value that goes with that x value, right? Now, what does that mean graphically? If I take those two values together, oftentimes we write them as an ordered pair. X equals 1, x comes first, and then y is negative 11/4. What does the graph of that look like? If I graph an ordered pair on the xy plane, what am I graphing?
1 and then relation 11.
Okay, but am I going to graph a line or a parabola or a point, or what am I graphing? A point, yeah. That's the point. If I go over 1 and up 11/4, I mean, I didn't graph these right, but it's going to give me a point on that line that has those coordinates, right? Okay, agree? So when I look for a solution of a line, I'm just looking for a value of x and y that make the equation true. How many of them are there on that line? How many points are there that make up that line?
1.
Just this one line. How many points? I'm going to make the other one red. This is getting too confusing. So the blue line, here's the red line. I'm talking about the blue line. How many points make up that blue line?
Just about
a lot. In fact, more than that. How many? Infinite. There are an infinite number of points on that line. So there's an infinite number of possible values of x that go with y that would work for that equation, right? I could use this one that I found. Another one I could use is if x equals 0, then y would equal negative 13/4. There's another example of another point that would be on that line. There's an infinite number of them. Now, in the same way, there are an infinite number of values that I could pick for the red line also, right? Well, let's do one quick one. There's an easy one. If I let y, we're looking at the red line now, if I let y equal 0, so I plug 0 in for y, I'm going to get 4x minus 5 times 0 equals 8. What's 5 times 0? 0. So how do I get the x by itself?
Divide by 4.
Divide by 4. So I'd get x equals 2. So I'd get the point 2, x equals 2, y equals 0, right? If I had graphed this right, that would be on the red line. I probably should have taken time and done that. But that's one of the infinite points that sit on the red line. Okay? Now, when I'm solving a linear system like this, I'm going to get back one answer, and we'll see this happening when we go through a couple examples. I'm going to get one x value and one y value, not an infinite number of x and y values, but only one. How come? How many points are there that are simultaneously at the same time on the red line and the blue line?
One.
Where is it?
The vertex.
Oh, well, maybe not the vertex. What do we call that? Vertex means something a little different. Intersection, yeah, right there. There is the single point where they cross, right? So that's the one value of x and y that works in both of those two equations. When we solve a linear system, that's really what we're doing. We're finding where they cross, okay? All right, so now that we know that, let's take a peek at this guy. Okay, so let's look at some methods we can use to find out where that intersection is without graphing, without having to look at a graph. How can we do this? Well, we can solve using two methods, the substitution method, which we'll look at first, and then the elimination method. The substitution method, I'm sure you remember doing this. This is the one that we want to use when we have at least one of the two equations in our system has what we sometimes call a naked variable, a variable that doesn't have a coefficient. It's either got a 1 or a negative 1 in front of it, which makes it easy to isolate, okay? That's when this one comes in handy. So here's an example. If I look at this system right here, can anybody spot an x or a y that has a coefficient of 1? Where is it? Oh, good. Okay, so right there. That's the one we want to isolate. It's easy to get by itself. What's the only thing I have to do to get that x by itself?
Get rid of the 2y.
Yeah, subtract 2y to the other side. Easy. Okay, so we'll do that. So if I subtract the 2y to the other side, there you go. Now I've got my substitution equation. Now somehow I think I lost my ability to write on this thing. I don't know why that happened, but I like to put a box around that. When you get the substitution equation, put a box around it because you're going to come back to it later, and you'll see why. So once we isolate one variable from one equation, in this case the bottom equation, then that's where the substitution comes in. We're going to substitute that equation into the top equation, that expression. We're going to trade all the x's in the top equation for a negative 2y plus 2. That's where the substitution comes in. And the beauty of that is, instead of having both x's and y's in the top equation now, we've made a good trade. We've traded that x for a bunch of y stuff. So I'm left with only y stuff in the top equation, which makes it easy. If we can pin an equation down to a single variable, it's easy to solve. That's the stuff we were doing yesterday. So we make the substitution. Instead of an x, we trade it for a negative 2y plus 2, and now that looks an awful lot like the stuff we did yesterday. Right? What would we do to solve for y there? Got to distribute. I've got multiple y's. I can't point to a single one yet, so I can't yet isolate it. I got to distribute. Oh, I guess they solved it already. Well, okay. If we went through that whole process of distributing and collecting like terms and isolating y, we're going to get y equals 5. But we're fine with that. That's what we did yesterday. You guys are doing fine on that stuff. No problem. So I've got one of the two parts. I've got the y value of the solution. That's the y value of where the two lines cross. How do I find the x value? Where's the easiest place to plug that in? And that's why I'm telling you should put a box around that substitution equation, because it's right there. Look, this one's already got x written in terms of a formula for y. So I'll just take that y value, plug it directly back into that expression, right? So instead of a y, we've got a 5. Simplify, and we get our answer, negative 8. Both parts. We got the x value and the y value. So there's our ordered pair. That's the solution. Negative 8, 5. X equals negative 8, y equals 5. That's the location of the point of intersection of those two lines. Make sense? Okay, so that's substitution.
Yeah.
Just doing it again. Oh,
Practice another one, right?
different problem. Okay, same deal. So here we're going to Oh, that's checking the solution. Yeah, so this is a good point. So how would we know the answer, or we think the answer is, what did we say it was, -8.5? How do we know for sure that that's going to work? How do we check?
Plug it in.
Plug it into what?
The X.
X and Y. Which equation?
The original.
Well, there's two original equations.
To the one on the left.
Doesn't matter. Okay. Now let's think about this. If I plug it into the top equation and it works, what's that telling me? You do. You're right, because all it tells me, if I plug it in the top equation, all that tells me is at that point it's on the top line somewhere, right? Does that necessarily mean it's in the bottom line?
No.
Got to find out. We got to plug it in the bottom one also. If it works for both of those, then I know it's a solution. So we got to plug it back into both this time. Okay? All right, so. Okay, the other method, they call it linear combination. A lot of times it's called elimination instead. This is the one you use when you don't have a nice, obvious substitution to make. You don't see an X or a Y with a coefficient of 1 or -1. Then substitution gets kind of tricky. It involves a bunch of fractions, and we'd rather avoid that. So there's another technique for it, linear combination. This is the one that says we could multiply either one or maybe even both of the equations by just the right number so that the variables line up in order to cancel. Okay, I'll show you what I mean by that. Let's take this example right here. Now, I don't see any X's or Y's that are easy to isolate. They all have numbers in front of them, coefficients, so we don't really want to use substitution here. None of those variables cancel if I add those lines up right now, but what could I do? You see a way that I could multiply either the top or the bottom by a number so that the X's would be an opposite number, or we'd have an opposite number of Y's so that they would cancel when I added them up? Okay, if I multiply what's the suggestion?
Jerry said 20.
20. I thought I heard a 2. 2?
Yeah.
What do I do with the 2? Okay.
What are we doing?
Okay, what we're trying to do, yeah. Let me try this again. I think that was confusing the way I said that.
I'm just confused altogether.
Okay. This is, let's go back a step or two. Now, this is not a good candidate for us to use substitution, because no matter what I do, if I try to isolate any of those variables up there, let's just say hypothetically, I want to isolate the X in the bottom one. I'm going to have to add 5y to the other side and then divide by 4. I'm going to get a bunch of fractions, right? Then I'm going to have to substitute into the other equation. That's ugly. We don't want to do that, right? So instead, our goal is we want to be able to multiply both sides of one of those equations, hopefully, maybe even both of them, so that I can get the variables to match up. Now watch what happens in this case if I multiply the top equation by -2. If I multiply the top equation by -2, the X coefficients are opposite. So they match up, but they cancel if I add them vertically. Okay? That's the goal. So I left the bottom equation the same. I multiplied the top one by -2 all the way through. Notice I had to distribute that -2 through all parts of both sides, right? Okay, now when I combine those equations, when I add them up, look what happens. The x's cancel. -4x plus 4x goes away. That's our goal, right? We want to get rid of a variable. If we can get rid of a variable, it makes this easy, right? That's our whole goal. So that's why we wanted to multiply the top one by -2. What about the rest of the stuff? The x's go away. Positive 8y plus -5y is 3y. -26 plus 8 is -18. That leaves us with a really simple equation to solve for y. Just divide both sides by 3, right? And I've got the y value. We're halfway there. So if I know what the y value is, it's -6. How can I find the x value? Okay, into which one of the original equations? Either or, doesn't matter. In this case, all we're trying to do is solve for x. It's going to work in both of them because we're trying to find the place.
So you only need to do both of them?
No, we're not checking the solution is different. If you're checking the solution, when we're all done, we got to plug both the x and the y value back into both of the original equations to make sure it works in both of them.
Alright.
But when we're just solving, we're just trying to find the value of x. I know what y is. So if I plug a y value into the top equation, that's fine. I'm going to end up with only an x there. If I plug it into the bottom equation, I'm also going to end up with only an x to worry about. It's going to work either way. I just want to pick maybe the easiest one. Which one has the smallest numbers? And there's not much difference in this case. Really, either one of them probably would be okay. We're plugging it into, what do? They plug it into the top one, okay? So if we plug in -6 for y in the top equation, look what I get. -4 times -6 is positive 24, right? And now what are the two steps I would use to get the x by itself? First I would subtract 24 and then divide by 2. Very good. Okay, make sense?
Yeah.
So that's my answer then. I've got a y value and an x value, so those are the coordinates of the solution, the point where the lines cross. Okay? Get the idea?
Yes.
Now in this problem up here, it was the best way to do this was to multiply the top equation by -2 because that made the x's cancel. Could I have, not that I'd want to, but could I have made the y's cancel?
Yes.
What would I do to make the y's cancel?
Times them both by.
Okay, now I can't do that. I can multiply both sides by something. But now I might have to tweak both equations this time. Right? And the way we did it was kind of nice because I could multiply just the top equation by -2 and get the x's to line up so they'd cancel. If I wanted to get the y's to line up so they would cancel, it's a little harder, isn't it? Ah, okay, good. If I multiply the top by 5, I'm going to get everything's going to change, but I'm going to get a -20y, correct? What would I multiply the bottom by then? How about -4, so I get a positive 20y? A -20y on the top and a positive 20y on the bottom, right? And then they cancel when I added them up. Now let's look at one where we have to do that. How about this guy?
Icky.
A little bit, right? Because that's not one, I don't have the luxury of being able to multiply just one equation by something here. There's nothing I can multiply 8 by, no integer, no nice, round integer I can multiply 8 by to get 12. And I obviously can't multiply 5 by any number and get 7 other than some fraction. We don't want to do that. We want them to be integers. Nice, convenient integers. So what are some suggestions here? What do you think? Yes, sir.
Times the top by, times the top y by 4, and then the bottom one by -5.
Okay, top by 4, bottom by...
-5.
Okay, now if I do that, let's look at this. If I multiply the top by 4, which ones are you trying to get rid of, the x's or the y's? I got to get where I can write on this thing. This is driving me nuts. Hang on. Okay, here we are. Okay, so here's the equation, right? God, I did it again. What is this thing doing?
It doesn't like you.
It doesn't like me. Oh well, I can't write on it for some reason. Okay, I've either got to get the x's to go away or the y's to go away. Right? I've got two choices here. Hey, listen please. How could I get the x's to go away? What's the smallest number that both 7 and 5 go into? What do you think, Jerry? Oh, 35. Okay, good. So I'd have to make the top maybe positive 35 by multiplying 5 all the way through. Everybody's got to listen to this closely. You're not going to get this. Multiply the bottom by positive 7 and get a -35, and that would work. The x's would cancel. Those are big numbers, 5 and 7. Could I accomplish the same thing with the y's using smaller numbers?
2 and 3.
Ah, 2 and 3, right? I could multiply the top by 2 and get -24y, and the bottom by 3 and get positive 24y, right? That's better. I'm multiplying by smaller numbers. That's going to make this easier to deal with. Everybody see that?
Yeah.
So if we multiply the top one by 2, look what we get. There's our -24y. If we multiply the bottom one by 3, look what we get. There's our positive 24y, and now we're set. When we add them up vertically, the y's cancel, right? I get 14x minus 15x is negative 1x. Negative 44 plus 42 is negative 2. If negative x equals negative 2, either multiply both sides by negative 1 or divide both sides by negative 1. Same thing. And I get x equals 2, right? Where do I go with that 2 to solve for y? X equals 2?
So you plug it into
One of
X.
the originals. Doesn't matter which one. We'll just plug it into, how about that one? Okay? Plug in x equals 2. I get negative 10 plus 8y equals 14. Add 10 to both sides. Divide by 8, I get 3. Okay? Okay, last example. Okay, if I go about this one, I could use substitution, right? Solve the first equation for x. Substitute it into the second. Okay, so I'm going to plug in that 2y plus 3 goes in for x. So if I distribute, I get 4y plus 6 minus 4y equals 7. Now, if I do all the math here, the 4y subtract away from both sides, and I'm left with an answer, 6 equals 7. We saw something like that yesterday. What did that mean?
No solution.
And no solution. Now, what does that mean if, okay, what's it mean? If two lines have no solution, do they ever cross?
No.
What kind of lines are those?
Parallel.
Sure. Okay, very good. Parallel. Okay, no solution. What about this one? If I go through the math on this one, multiply bottom by 5, top by 2, or other way around, top by 5, bottom by 2, the y's cancel. And this time I get everything cancels, not just the y's. I get 0 equals 0. What did that mean yesterday?
Infinite solution.
Okay, that meant infinite solutions. So what kinds of lines intersect always at all values of x?
0, 0.
Same line, lines that overlap. If it's the exact same line, then they have all points in common, right? Make sense?
Yeah.
Okay, let's head down, get a little work done. 205.
Yeah, a little work.